Hello everyone and welcome to the ENA exam review number 1 in spring 2023. In this one, I'm just going to go over the basics, which is like a review. So we're going to go over voltage, current, resistance, and power. And then we're going to review Kirchhoff's laws. And then after that, we're going to do a bunch of problems on resistor networks. So first, we're going to derive the equations for the voltage divider and current divider. And then we're going to go over a bunch of different techniques to solve resistor networks. All right, so let's get started. Just to review the basics. So voltage is the electrical tension or pressure that pushes the current through the circuit. So the most basic form of voltage in our circuits is just a dependent voltage source, which means the current flowing through this voltage source does not affect the voltage across it at all. So no matter the current flowing through this voltage source, the voltage V will always stay the same. But that's not the case for dependent sources. So there's two kinds. The first kind would be a voltage controlled voltage source, which means the voltage V is multiplied by another voltage Vx, which is a voltage drop somewhere else on the circuit. So this voltage drop somewhere else in the circuit will depend or change this voltage V depending on the value of Vx. So that's a voltage controlled voltage source. It's a function of Vx. V is a function of Vx. So the other kind is a current controlled voltage source, which means the current flowing through it, I, controls, I'll call this Ix, and this will be Vx, and then that means the current Ix flowing through here multiplies the voltage across it. So depending on the current flowing through this voltage source will change the voltage across it. So it's a function of Ix. This is a current controlled voltage source. So likewise for current, so current is the amount of charge that's flowing through a conductor like a wire. So just like the voltage sources, we also have current sources, which just push out a current I regardless of the voltage across it. So regardless of the voltage across it for the dependent current source, the current will always stay the same. And just like controlled voltage sources, there are controlled current sources. So I'll start with the voltage controlled current source, which depends, or it's a function of Vx. The current changes depending on the voltage across it, which is Vx. So this is a voltage controlled current source. And then the other kind would be a current controlled current source, which means the current flowing through this current source changes how much current is flowing in the source. So for this one, it's a function of Ix, and it's a current controlled current source. Nice. So next, just resistance, which is the opposition of the flow of current, and where that current goes, that's lost, it's energy that's dissipated through heat, so it becomes heat. So we use resistors to limit the amount of current flowing in a piece of wire. And we all know if current's flowing through a resistor, then there's a voltage across it, or vice versa. It's all related through Ohm's law, which is V equals I R. And so next, power. So the state equation is just P equals I times V, but then we can also substitute for voltage or current using Ohm's law. So that means P could be either V squared over R, or P is equal to I squared R. And then you would use these two equations with R, the ones with R in it, when you know you have like a specific load that's dissipating heat, such as a resistor. All right, on to the next. We're going to talk about Kirchhoff's laws. So the first one is Kirchhoff's voltage law, which states that the sum of voltages in a closed loop equals 0. So in this circuit here, it's in a closed loop, so current's going to flow in this direction out the positive terminal, and then across these 4 resistors, there's going to be 4 different voltage drops. So the KVL states that the voltage source is equal to the sum of the voltage drops across each resistor individually. So that means the voltage source V equals the voltage across R1 plus the voltage across R2, and so on. And then the KCL says that the current flowing into a node, the KCL states that the current flowing into a node equals a current flowing out of the node. So let's just say, for example, we have 3 currents flowing into a node. I1, let's say this is I2, and this is I3. So since in this node right here, with similar by this dot, each of these 3 currents is flowing into the node. So I1 plus I2 plus I3 is equal to current flowing out, which is in this diagram, I drew no currents flowing out, so it's 0. That's Kirchhoff's current law. So we're going to use these 2 laws to derive the equations for the voltage divider and current divider. So for the voltage divider, knowing that these resistors and voltage source connected in series, the current flowing the circuit I is going to stay the same. So when I write the KVL, that's going to say Vn is equal to the voltage drop across each of these 2 resistors added up. VR1 plus VR2. And then notice that the current is staying the same. So we want to write these 2 voltages across the resistor in terms of current. So we have the current I times R1 plus I times R2. That's just using Ohm's law. And see, we can factor out the current I. I'll just factor out like this. That means I is times the quantity R1 plus R2. And then now the trick is I need to solve for the current I, which is going to be Vn divided by R1 plus R2. And notice that when I take this I1 and multiply it by each of these 2 resistors, I'll get its voltage across it in reference to this point I just put here. So notice when I multiply this I, which is staying the same because it's in a series circuit, this I times R1 is exactly the voltage across R1. So let's go ahead and replace that. That means VR1. Well, I also have to multiply this side by R1. This is going to be R1 over R1 plus R2 times Vn. And so this is basically the general equation for a voltage divider. It just states that the voltage drop across a particular resistor in this voltage divider is equal to that resistor value divided by the sum of n, or how many, depends how many resistors you have, it could be 10, times Vn. So yeah, that's a general equation for a voltage divider. And very similarly for a current divider, this one instead we're going to write a KCL. So this is going to be I1, should say this is I2, and then this is I3. So I1 is just IN, so I'll write the KCL, which is going to be IN is equal to I2 plus I3. I2 plus I3. And now, just like the voltage divider, I need to write these 2 currents, I2 and I3, in terms of voltages. So IN is going to be using the fact that this is a parallel connection. So at this node, the voltage reference to ground is staying the same in the circuit throughout. So that voltage is also going to be dropped across here, the same voltage, reference to ground. So it's going to be V over R1 using Ohm's law plus V over R2. Then I'll factor out a V. So IN is going to be V times 1 over R1 plus 1 over R2. And so we can use the fact that 1 over R is also called the conductance, which is usually denoted by G. So for R1, I'll replace with 1 over R1 replace with G1, and then 1 over R2 is going to be G2. So IN is equal to V times G1 plus G2. And then now I'm going to solve for V. Do that little trick. So V is going to be IN over G1 plus G2. And then notice that when I divide by a particular resistor, then I'll get the current that's flowing in that branch. So this would exactly be I2. So I2 is going to be equal to, so I'm dividing this thing by R1, which means I'm multiplying by G. So it's going to be G1 over G1 plus G2 times the input current. And this is the general equation for a current divider using the fact that G is 1 over R. It's very similar to the voltage divider, except we're working with conductances. Next, we're going to go over nodal analysis. So now we're entering some of the basic techniques to solve resistor networks. So nodal analysis, the basis of it is KCL. So what you're trying to do in nodal analysis is you're trying to find voltages across nodes. So you want to find out what are these node voltages, because once you know the node voltages, you can find the current flowing in that particular branch. You'll just do V divided by R, because R always stays constant. So when you write your equations using KCL, the number of unknown nodes you have will be the number of equations you need to solve. It's going to become a linear system of equations. So you're going to have n unknown nodes, which gives you n equations. So how to set it up is, I noticed that this is a node because current will flow here, which I'll call I1. It could flow this way, which I'll call I2. Oh, sorry. I2, and it could flow this way, which is I3. Or rather, I'll label the resistors, it's a little weird, so I'll change this to I3 and the other one I2. Okay, just to stay consistent. So this is I3 and this is I2. So writing a KCL, current flowing in is current flowing out, so that means I1 plus I2. These are two currents flowing into the node and flowing out of the node. That means equals I3. And then what do you need to do after, so this is the KCL, which is this equation. Now you need to write these currents in terms of voltage. So you can introduce R into the equations. So I1 is going to be, what you're going to do with this, let's just say this is V plus, this is V minus, this is just for R1. So the voltage across R1 is going to be V plus minus V minus divided by R1. So it's V plus minus V minus divided by R1. And that's exactly I1. Using the same logic, I2, so I'll just keep these, here, it'd be easier if I did this. I'll just label these node voltages like V1, V2, and V3. So let's say this one on the left is V1, this middle one's V2, and this right one is V3. So I just need to rewrite this. So it's V1 minus V2 over R1. And how I know how to subtract it in this order is because I'm looking at the direction of the current. Since the current is flowing from left to right, I go from left to right on the node voltages. So it's V1 minus V2 from left to right, and then divide by R. So that means I2 is going to be V2 minus 0, because this point in the circuit is ground. So that's V2 minus 0 divided by R. Oh, sorry. That's the wrong one. I was looking at the middle one. I2 is on the right. Sorry about that. So for I2, it's going to be, yeah, sorry about that. I2 is this current right here. So it's going to be V3 minus V2 divided by R2. And that's I2. And then I3 would be this current flowing down here from V2 to ground. So that means it's V2 minus 0 divided by R3 is equal to I3. And so that's how you do nodal analysis. So in this case, we have one unknown node, so we're going to have one equation. So it's just going to be these three summed together. So let's go ahead and take a look at an example. So this one, we needed to use nodal analysis to find the current I0 in this circuit. So we'll go ahead and redraw this or just make it bigger, like this. Then we can just get rid of this. So we need to find I0. Okay, sorry. So in this circuit, first thing we need to do is pick a place of reference, which is our voltage reference or ground. So I'll just pick it here, usually pick it at the bottom. And then we need to label our nodes. So current can split there, it can split here, and it can split here. I'll call this one VA, this one here VB, and this one VC. All right, now we have our nodes label. I can draw some currents. So let's just call this one here I1, and say this one's I2, and then we already have I0 labeled for us. That's what we're gonna solve for. Let's say this one's I3. So we have three nodes, so we're gonna have three equations. But first thing we should notice is that this node here, VA, is exactly 60 volts. Because this source, the plus, is connected to this node, so it's gonna be 60 minus 0, so there's 60 volts dropped on that node. So VA is gonna be 60 volts, and that's gonna be equation, that's equation number 1. It's like a given, like a little gift. That's very nice. So now I need to look at these two nodes, VC and VB. I'll go ahead and start with VB. So I need to write the KCL at the node VB, which is just current going in equals current going out. So at VB, there's just three currents going in and 0 currents going out. So it's gonna be I1 plus I2 plus this current source 3 I0 dependent current source equals 0. And then rewriting these in terms of voltages, I1 is gonna be VA minus VB. I should probably replace VA with 60. That'll make things easier. VA is 60. This is divided by 10. That's I1. And then I2 is going to be VC minus VB divided by 2. VC minus VB all divided by 2. Then the last current, 3I0, is going to be the number 3 multiplied by I0, which is VA minus VC divided by 4. VA is 60 minus VC over 4. And this is all going to equal 0. This is equation number 2. And then for our last equation, I need to write the KCL at VC. So let's go ahead and do that. So we have the KCL at VC, which is going to be I0, because that's flowing in, equals current flowing out, which is I2 plus I3. So I0 is the current flowing in, equals current flowing out, I2 plus I3. And then rewriting these equations, I0 is 3 times 60 minus VC over 4 equals I2, which is VC minus VB, over 2. Then the last one, I3, is going to be VC minus 0, because that's reference, VC minus 0 divided by 8. divided by 8. And this is equation number 3. So I have these system of equations, 3 equations, one of them was given. So I'm going to look at equation number 2 and number 3. I noticed that it's exactly 2 equations and 2 unknowns. My 2 unknowns are VC and VB. And so you can either solve this however you like, MATLAB, you could use like back substitution and all that. But now that these equations are written, it's no longer a circuit problem. This is just an algebra problem. So I'm not going to spend any time on those because it's just like, it's just really tedious because we want to solve systems, you can solve however you want, matrix, TI inspired, but anyway. The problem wanted I0, which is just 60 minus VC over 4. So when you solve these 2 systems of equations, you'll get the value VC, so you just plug that in here, and then you'll have the current I0. And that's how you solve this circuit. And so next, the other method is mesh analysis. So for mesh analysis, the basis of it is now the Kirchhoff's voltage law, and instead, the number of meshes will be the number of equations you have. So it's going to be another linear system of equations. What I mean by mesh is it's a loop that does not depend on or not interact with any other loops. And so what you're trying to do in mesh analysis is you're trying to solve for the branch currents or the currents flowing in these meshes, the mesh current. So, oops, I put I2, 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 sorry, this is I1. So what you're doing in mesh analysis is you're writing instead a KVL like this. So how you write these equations is you write a KVL. So with this KVL, I see for I1, it's going to be the voltage drop across the voltage drop across the first resistor plus the voltage drop across the second resistor equals 0. And then you write them in terms of currents. So mesh I1, so VR1 is going to be R1 times I1 plus, because I'm going into this plus sign, plus, so the trick with neighboring branches is you're supposed to subtract the mesh current from the neighboring mesh, because you don't want that current. You want the current from the mesh you're focused on right now. So you need to subtract the one that you're not looking at. So that's going to be I1, which is the mesh I'm working with, minus I2, which is a current I need to subtract because it's neighboring. Because how to look at it is you have this branch, and then you have I1 going this way, and then I2 is going this way. So if I want I1, I need to take I1 and subtract it, or sorry, I2. I need to take I1 and then subtract it from I2, and that'll give me I1. And this is going to be multiplied by the resistance equals 0. And then mesh 2, likewise, will just be the voltage drop R3. It's going to be I2. Oh, sorry, no, wrong. It's supposed to be R2, or R3, sorry. R3 times I2 minus I1. That's this voltage drop across here, plus VR2, which is just R2 I2 equals 0. So yeah, this is the basis of mesh analysis. So let's go ahead and look at an example for mesh analysis. So we need to find V0 in the circuit below using mesh analysis. So let's go ahead and make this bigger. There we go. Let's get rid of this and make this big. There you go. So do you, here, let me go ahead and do this, sorry. Gotta make it really big. There you go. So we need to solve for V0 using mesh analysis. So I'm gonna draw my 3 mesh currents. Let's say this is I1. Let's say this current's I2. Let's say this one is I3. So I'll first write the KVL at I1, or mesh I1. So that's going to be, following this arrow, I go into the negative of the voltage source, so I need a negative 20 volts And I'm gonna go ahead and just draw some polarities across these resistors like this. As so. You just need to follow the polarities of the resistor. Good. So I get a negative 20. I'm going into the plus 2 times I1. There's no neighboring mesh. And then plus that resistor 1 times the current I'm working with minus that other mesh current, which is I3. And then I need this last voltage drop, which is going to be plus 2 I1 minus I2 equals 0. So that's equation number 1. So second equation, I'm going to write the KVL for I2. So KVL at mesh I2. I'll just start from this point right here. So I get a negative 2 times I2 minus I1. I'm just starting at this point down here and going up. And then I get a plus 4 times I2 minus 10 equals 0. That's going to be equation number 2. And then equation number 3, I write the KVL at I3. And the thing about I3, we should notice that there's a current source here. And remember that this is, so specifically this is a dependent current source. So that means in this mesh here, the current I3 is simply given. It's 5 amps flowing in that mesh. So with this 5 amps, I can go ahead with anywhere else in this system of equations. I can replace I3 with 5. Replace I3 with 5. So there's I3 there, which simplifies our equations. So notice that we have 3 equations and some unknowns. We had 3 unknowns, but one of them is given. So now we have 2 equations and 2 unknowns. This is equation number 3. So the unknowns would be I1 and I2. And what you're going to do with I1 and I2 using mesh analysis is we notice that V0 is going to be I times R. So depending how you're looking at it, the current flowing in this branch is going to be I1 minus I2 times 2. And that should be the voltage drop across this resistor. It's going to be V0, this is ground. Or in other words, it's just V0. Oh, sorry. The current specifically flowing in that branch, you have to write a KCL. So yeah, I guess in this problem, there's like a little extra step you have to do. So we notice that, I'll just call it I0. That I0 is going to be V0, I need to put it ground here, minus 0 divided by 2. So I0 is going to be V0 over 2. And then I0, depending on your perspective of it, will be either, well, yeah, it doesn't really matter. It's like a neighboring mesh, so it could be either I1 minus I2 or like vice versa. Just depending, you just have to stay consistent with your arrows. But yeah, once you solve your system of equations, you just need to plug it in to this right here, and then that should be the voltage V0. All right, next will be the Thevenin's and Norton's theorems, I think. Let's see. Yes, it is. So Thevenin's and Norton's theorems, or it's just one theorem, or 2 individual theorems. It states that any resistive network can be simplified into these 2 very simple circuits. So there are a couple constraints. There's 3 of them. So the 3 constraints are the networks can only contain dependent voltage and current sources and resistors. That means using these theorems, you can simplify these 2 really complicated circuits into these 2 forms, which are very simple to deal with. So the Thevenin equivalent would be a voltage source in series with a resistor, and then the Norton equivalent is a current source in parallel with the resistor. And how you calculate these values, the Thevenin voltage will just be the voltage, if you see this black box, seen from the circuit itself. So what you need to do is you basically need to zero all your sources to find this resistor. So in this case, they have it written as RTH and RNO. Well, they're going to be the same value. It's just the equivalent resistance. And then the Thevenin voltage and the Norton current are calculated by zeroing the sources in these two circuits. And then you solve it via that. You have to add them algebraically, knowing that current sources add up in parallel and voltage sources add up in series. And then it can greatly simplify the circuits into these two forms. So that's Thevenin's and Norton's theorems. And then source transformation would be the process of going between these two types of circuits. So remember, the Thevenin equivalent looks something like this. Look like this, where that's the Thevenin voltage, and this is the equivalent resistance. And then we want to go between this and this, the Norton equivalent, which this is I, NO. And then we have RTH. Oh, sorry, it's supposed to be in parallel, sorry. Like this. It's connected across it. And then we have the output seen here. Let's just say it's V out. This is REQ. And so we wish to transfer between these two circuits. So how you do that would just be Ohm's law, which is very nice. It says VTH is equal to REQ times I NO. So that's how you solve for the Thevenin voltage, or in other words, the Norton current is going to be VTH over REQ. So these two equations are the ones you would use to transfer between these two circuits, called source transformation. It's a really powerful tool to solve resistive networks. Another powerful tool would be the superposition theorem, which basically states that the sum, I know this is going to sound really confusing, but I'll explain it. It's the sum of the individual outputs evaluated at its inputs individually is also equal to the sum of the inputs by itself, and then you evaluate it at the output. What I mean by that is, in a system, you could either have f of, let's just say you have an input x plus 1, you have another input x plus 2, and then f of x plus 3. So x1, x2, and x3 are inputs, and then they're all evaluated at your function f, which is your output. Well, you could either do it like this, where you can evaluate each input individually and then sum them up, or in a linear system, you could either evaluate each input individually, like this, and then evaluate it at your function. So the superposition principle states that these two quantities have to be equal to each other. You can do it either way. So how this works in circuits is, in a circuit, if you have voltage sources and current sources, two different kinds of inputs, you could either solve the circuit just as a whole, considering both sources, or you could zero one of the sources, then solve it, and then zero the other source, and then solve it again using just that source, and then you add those two quantities together. That's what the superposition theorem in circuit says. So first you pick either a voltage source or current source, excuse me, to zero it. What I mean by zero it is a voltage source becomes a short because voltage does not drop between a short circuit, and then a current source, you open it because current can't flow in an open circuit. So it's almost like two little processes rather than one really big one. It's like breaking it apart. So let's look at an example. Use the superposition principle to find I0 and V0 in the circuit shown below. So let's go ahead and resize this. That was bad. Let's see, do that again. Like this. Let me go ahead and get rid of this. So we wish to solve, oh, that's not good. We wish to solve for, here, I'll just do this. We wish to solve for I0 and V0 using superposition. So how are we going to do that? Well, first we have to redraw the circuit by zeroing one of the sources. So I'll go ahead and zero the voltage source, which basically it would take this circuit and make it, or it would take this voltage source and make it a short basically. So it would look, instead of this here, we'd have a short, and then I'll evaluate the circuit like this with the current source. So you can use either, or any kind of technique you'd like. I like to use nodal analysis. So this is VA, I'll just label VA, VB. So I'll write some KCL. First I need the KCL at VA, which is going to be, this is I1, let's just say this is I2, that's I0, and this is 4I0. Let's say this current here is I3. So KCL at VA is going to be current going in, which is I1, equals current going out. So that's I2 plus I0. And so rewriting this, I1 is 6 amps because there's 6 amps flowing into here. So that's going to be 6 equals I2. Oh, I need to pick my ground. Sorry. It should always be first. So that's going to be I2 is VA minus 0 divided by 40 ohms. That's I2. I3. Oh, sorry. I0. Sorry. That's going to be VA minus VB divided by 10. And that's going to be equation 1. Now the other equation, I just have one more node. So I need the KCL at VB, which is going to be current going in, I0 plus 4I0 plus I3 equals 0. And then I0 is VA minus VB divided by 10 plus, I know the current flowing into there from this that's just going to be 4 times I0, and I0 is VA minus VB divided by 10 plus I3, which is 0 because it's going in this way, 0 minus VB divided by 20. That's equation number 3. And then you solve those, and then you're gonna get from those, so let's call it parts 1, we solved for VA and VB. And once you get VA and VB, you can solve for I0, but it's not quite done yet because we also need to evaluate this circuit by zeroing the current source. And then we have to look at it from there and then sum up those quantities. So if I remember correctly, this was a, I can't really remember. Let's just do this real quick. I probably should have written it. Oh, can only go back so far. Well, let's just say it was, I forgot, sorry, that's really embarrassing. I'll say it was like, I think it was like negative 20 volts, like this. Hopefully that's right. Something like this. I think it was 20. We'll go with that. So from part 1, we solved for VA and VB. Well, I didn't, but you can solve that linear system of equations however you'd like. Oh, what am I doing? Yeah, so the second part would be to zero this current source by making it an open circuit. And so you realize when we make this current source an open circuit, that just deletes this whole part of the circuit, but we'll still have this resistor here. So what we're doing is we're just going to take this whole chunk of the circuit, and then it's non-existent. So these branches are gone too. Now we need to evaluate the circuit using this configuration, and I'll go ahead and use null analysis again. So this node's going to be -20. I guess I'll start with VA. I2 is going here. Well, now, or no, actually now we just have one node, and we should just have one equation. We just have one unknown VB. So I'll write the KCL at VB, which is going to be I0, or sorry, they're all going into the node, so they're all going to add sum to 0. I0 plus 4 I0 plus I3 equals 0. So I0 is going to be this voltage here, which is, it's going to be, there's no voltage there, there's going to be no voltage drop there. So 0 minus VB over 10 plus 4 I0, which is 0 minus VB divided by 10 plus I3, which is -20 minus VB divided by 20. And then this is just going to be equation number 1. We just need to solve for VB. And then what we need to do now is, now that we have this VB, this is going to become VA plus VB plus VB. Because this is part 1, and then this is part 2. We have to add these two parts together. And then you can solve for that voltage, which is going to be VA minus VB. And VB is just 2 VB, so that's going to be a number. So yeah, all you need to do is, that's how you do superposition. And then, honestly, the part that takes the longest would be solving these system of equations. It's just a lot of algebra and it's really tedious. But yeah, that's how you do the superposition principle. So lastly, we're going to go over operational amplifiers. So what they are, they're like analog computers because they compute. They can add, subtract. They can even do complex math operations like differentiation, integration, also logarithm and exponentiation. But yeah, but basically the basics of them is they're a 3-terminal circuit element, and they can produce a gain, which in other words, they're an active element. So the golden rules of an op amp, they have some golden rules, is that no current can flow into either input terminal. What I mean is, so the op amp looks like this. It has 2 inputs, namely the inverting terminal and the non-inverting. So we all know the minus is the non-inverting, or sorry, the minus is the inverting and the plus is the non-inverting. So let's just say this is V minus and this is V plus, just staying consistent with these signs. The voltage across these two terminals at all points is always 0. Therefore, the current flowing into the op amp is 0. So I just drew those currents I1 and I2. They're both going to be 0 amps. And then V minus is going to be 0, which equals V plus. Therefore, V plus minus V minus is also equal to 0. So these are the golden rules for an op amp. I'm not going to go into too much like why it's like that. It's just how it is to practically model these devices. But that's the golden rules in op amp. But if you're wondering how it produces gain, what's not shown are these power terminals that power the op amp. So current can flow from in and out of the output terminal of the op amp. And practically speaking, it goes through these power terminals of the op amp. So it needs to be powered in order to produce gain. So let's go over an example. For the example, we'll just derive the general equation for a basic inverting op amp configuration. that produces gain. So you have to provide something called negative feedback, which is basically an impedance that is fed from the output back into the input. I'm not going to go into too much detail like why you do that, but it's just a method of producing gain. This is ground. Let's draw this as Vin, this potential here. This potential is connected to ground, and then this potential here would be V out. And then this resistor we'll call R in, which is just input resistor, and then RF for R feedback. So using the golden rules, the current flowing into these two terminals is 0. But we know that current can flow this way and this way. So I'll call this one I1 and this one over here I2. And I'll write the KCL at this node VA. So KCL at VA. Okay, so using KCL and the golden rules, you have to consider both of them. Since current can't flow into the op amp, this really isn't a node, because this I1 will just flow like this, and this I2 will flow like this. It can't go into the op amp. Therefore, VA is going to be a potential of 0. Hope that makes sense. But writing the KCL, that just means I1 is negative I2. In other words, I1 plus I2 equals 0. And then now, using nodal analysis, I need to rewrite these currents in terms of voltage. So I1 is going to be Vin minus VA divided by Rn. Vin minus VA divided by Rn. And I2 is going to be Vout minus VA divided by RF. Divided by R feedback. And I wrote those using nodal analysis and the fact that current can't flow into the input terminals of the op amp, but it can flow, so it can only flow like as these arrows shown. So I'll just trace my cursor to make sure it makes sense. So it's flowing up through here, through this resistor, down here, and this way. And then I1's flowing the opposite way of that same track. So using that fact, we know VA has potential of 0 because current can't flow into the op amp. So VA is 0. So then our new equation is Vin over Rn is equal to Vout over RF. And then typically you want to solve for your output voltage because you want to know what your output is. So Vout is simply going to be, oh sorry, this equals 0. I skipped a step, sorry. I subtracted this part from both sides. So that's going to go here. So I need a negative sign here. Sorry about that. I still just went a little too far ahead of myself. So yeah, all I did here was subtract Vout over RF on both sides. So I get this new equation here. So that means Vout is going to be negative, if I do some algebra, negative RF over Rn times Vn. And this is what you call your somewhat of like a transfer function or your Vout to Vn relationship. Similarly to what we saw in the voltage divider and current divider, that your outputs to your inputs. And why you do this, if you think about it, if you take every possible output value and divide by your input value, you'll get a good understanding of how your circuit will react given this equation here. So this is the so-called transfer function of the circuit. In other words, it produces gain. As you can see, this one you can produce a gain larger than 1, unlike the current divider and voltage divider, because in the denominator you have a sum of the impedances. This one, we have RF divided by Rn. You can simply just make RF greater than Rn, and you'll multiply that number by Vn. You see this number here is simply a number that's multiplying Vn, which is also called the gain. So that's it for op amps. I think that wraps up our review we just went over some basics and then Kirchhoff's laws, and then we talked about resistor networks and then some op amps. So I hope that was useful or helpful for anyone watching. Thanks.